you want to ask something, let me know. So we basically had a look at electrostatics, where we said, okay, we have a charge and another charge, and let's make this one positive and this one positive. And then from grade 10, maybe you can remember, we said that they are on an insulated stand each, which means basically just that we say that there's charge conservation, which means no charge is lost outside of this closed system. Okay, so these two charges do experience a force between them. That is known as Coulomb's law. So Coulomb's law, remember, charge, this is actually from grade 9. I equals Q over T. We can rewrite this formula as Q equals I times T, which means charge is the current multiplied by the time. But we are talking here about charge, and we are talking about something that's measured in Coulomb. The symbol is C. Now this is confusing to people, and I'm mentioning it only because when we get to current, it's the amount of charge that flows by a certain point per second or per unit of time. So the important thing is Q, which we are looking at here. So we have two Q charges, and they are going to experience a force. So the force between them is called an electrostatic force. So we use Coulomb's law, which is F equals K Q1 Q2 over R squared. Now this formula is very similar to Newton's universal law of gravitation, in the sense that the force of gravity was equal to G M1 M2 over R squared. What's the difference between the two? Force of gravity is always a force of attraction. Force of gravity has never pushed anyone off planet Earth. That would be nice, but it doesn't work that way. So, whereas the force between two charges can be a force of attraction or repulsion. So in this case, we have two positive charges. It's going to be a force of repulsion. Very important when you use this formula, you do not substitute the symbol or you do not substitute the sign into the equation. If this was plus 4 microcoulomb, this was plus 6 microcoulomb, we would simply substitute 4 times 10 to the power negative 6, 6 times 10 to the power negative 6. And then another difference between Newton's universal law of gravity and Coulomb's law is that we measure gravity from the centers of objects, while we measure Coulomb's law as the distance between two objects, not from the centers. So that's just another important difference. Okay. Oof, yeah, the captions are killing me. Anyway, so this is a very important distinction that we need to make. Why? Because objects normally are not ground in real life. If you imagine yourself, you know that you have a center of gravity. Somewhere in your body, if that point is not balanced, you will fall over. Okay, so that's why there's a distinction between it. Then we looked at something called electric field. Now, electric field is a way to measure the strength of the force between these two. So, if you imagine that these are two rivals, and there's a field between them. You know, when you have a rival or somebody that you have the same charge as, there's this field between you. But somebody standing in the middle of that or somewhere in between the two of you can measure the field, the force. Okay. So we started to look at electric field, and electric field is a region in space where an electric charge experiences a force. So instead of using Q1 or Q2, we use a tiny point charge. We call it lowercase q. And let's say we place lowercase q a certain distance away from this charge and a certain distance away from this charge. We can go and calculate the net force that will be experienced by this little point charge. Point charge is always positive. we leave out the size of the charge because it actually cancels out. That was something that we focused on, which I just want to take you back to quickly. If you go and look at electric field, it is the force experienced by the charge, being this point charge at that certain point. So we can rewrite this formula as F is equal to E times Q. F is equal to K, Q1, Q2 over R squared, and F is also equal to E, Q. So these two are actually equal to each other. Now we're focusing on electric field over here. So instead of Q2, I'm going to call this charge Q. So I'm not focusing on these two, I'm focusing on these two. Now, if F and F are the same thing, it does mean that EQ is going to be equal to K Q1 times Q over R squared. The Q's cancel out, and therefore electric field is also equal to K Q1 over R squared, which means if I want to determine the electric field that Q experiences at this specific point, I am only interested in the size of this charge, Q1, and the distance between this charge and the point charge. And this is how we calculate electric field. Now, because this charge is in between two charges, it will experience a field, electric field over here, and it will experience an electric field over here. So we can calculate both of these. I'm not going to go to the calculation of the substitution part, that's not what we're doing here today. But you can calculate this answer, electric field, and you can calculate this answer, and then it's similar to solving vectors in one dimension. Let's say this value was 10 Newton to the right, because both of them are positive, because Newton's one to the right, and this was 5, let's make this 5 Newton to the left, because both of them are positive. So 10 Newton to the right, 5 Newton to the left will give you a net field of 5 Newton to the right, and therefore this point charge will experience an electric field that is going to be 5 to the right. Okay. This one charge will experience that it's going to be 5 kilolight. I'm going to turn this off because I will not be able to focus. I hope you've been laughing at home just a little bit. I can't wait to watch this. Okay. So that's the connection between electric field and electrostatic force. So electric field is actually Newton per charge, but as you can see here, we can calculate electric field as KQ1 over R squared. So your final unit is going to be Newton per coulomb. Newton per charge, Newton per coulomb. Okay, so the electric field here, let's say it was 10 Newton per coulomb. Both of them are positive, going to the right. In these two, it was 5 Newton coulomb. Because it's positive, it will be to the left. 10 minus 5, my net field will be 5 Newton coulomb to the right. That makes it. Okay, so electric field lines are very similar to what are they called? Magnetic field lines. So electric field lines, if you have a positive charge like this one, the electric field lines will always point away from this charge at a 90-degree angle with the surface. This means that if I place a point charge Q over there, it will move away. That's what these field lines actually indicate. If this was a negative charge, it would be pointing towards it, always. And therefore we can go and we can draw, similar to the magnetic field lines, we can go and draw electric field line diagrams where we have, if you have a positive charge and a negative charge like this, it will flow from the positive to the negative. If both of them are positive, they will just both flow away from each other, never touching, and if both of them are negative, they will flow um, towards each charge, but never touching. So that is something that you just need to be aware of in terms of drawings and diagrams. Okay, and then for both electrostatic force and electric field, we practiced questions where we had, similar to this, solving it in one direction, but also then combining it with term one work, where we figured out how to solve vectors in 2 dimensions. We're applying that knowledge to this section, which means that if you have vectors, and now it's no longer vectors, but forces in 2 dimensions, we can go and we can solve those equations. So this applies to both electric field and electrostatic force. If you have a charge, I'm doing electrostatic force first, over there, charge over there, charge over there. You can go and calculate the electrostatic force between these two. F equals K Q1 Q2 over R squared, and come up with a value. Remember, we don't substitute the signs, we omit the sign. It will be a force to the right. Why? Because both of them are positive. If we go and calculate the electrostatic force between these 2 charges, we'll come up with an answer using Coulomb's law, and because both of them are positive, we omit these signs, but it tells us it's a force of repulsion, it will be upwards. And now we basically have 2 lines for which we can go and draw a resultant. One way you can do it is the parallelogram method, like this. Another way in which you can do it is in detail. So there's this line, and then I'm adding this line, and this is my resultant. Doesn't matter which method you use, this still is going to be your resultant. This is it also going to lead you to use Pythagoras to solve R, and then you have your resultant. Okay. And then similarly, we did the same thing where we didn't calculate electrostatic force. I'm just going to change this so there's no confusion. But we calculated electric field. So this is point charge Q, which means instead of using Coulomb's law, to calculate the electric field, E equals K Q over R squared, where we use this sign, this size for Q, we omit the sign, and between these two, we will also use E equals K Q over R squared. We use the size of this charge for Q. Remember, the point charge, the size doesn't matter. And then we would come up with more or less the same result in terms of vectors or forces here. And then we would have to calculate the resultant in a similar way. So the main difference here being the formula that we use. And remember your R squared. A lot of students forget to square the value or the distance between the two. And that's basically what electric field strength was all about, what Coulomb's law was all about. How does this tie into electromagnetic induction? Okay, so this is how it works. We know that if I have a current carrying conductor, so I have a wire and it carries current, but there's actually a magnetic field around that wire. Now, having it in just 2 dimensions is too difficult to work with. So I want you to imagine if the wire is coming out of the board towards you, and we represent that with a dot. And if the wire is now looping, which it can, or it can be a separate wire going into the board. It looks like the back of a dart. If I were to throw a dart into the board, we indicate it with a little X. When we go and we draw the magnetic field lines, not electric field lines, magnetic field lines. For this one, closer to the charge, they are more concentrated, but then when we move further away, the space between the magnetic field lines actually increases. Okay, we'll do the direction in a moment. So if it is coming out of the board, you use your right hand, you point your thumb in a direction in which the current is flowing, and then your fingers will show you in which direction the magnetic field lines are going to be. Yes. Okay. If it's going into the board, I point my thumb into the board, and this will be the direction of the magnetic field. Okay. So sometimes we'll have a wire, and I'm going to try and draw it. This is now a wire that's going out, the wire is going in. Sometimes what happens is they have a loop. So a wire will be, and I'm going to try and draw this, coming out of the board and then going back to the board. So the current is flowing in this direction. Okay, so this is called a loop or a coil, and then there might be current associated with it. So there is going to be a magnetic field all around this wire in 3 dimensions. Okay, so that is the basics of understanding how we determine the direction of the magnetic field lines around a current carrying conductor. Then what we said was, what about if you have, let's say, a piece of metal and you coil wires around it. You try and just draw it so it seems as if it's going around the back. And you did an experiment perhaps like this in grade 9, with the metal on the inside was an iron nail. You wrapped copper wire around it and connected the copper wire conductor to a battery or cell, and then that piece of metal or whatever it was became magnetic. So what we see here is, if there's a current carrying conductor, it's actually going to make this metal on the inside, as long as it's a metal that can be magnetized, it's going to make it a magnet. How do we determine the north and south of this magnet? So what you need to do is, in this case, you see we use the same principle, right hand, which with our fingers, we indicate 4 fingers whether it's going over that metal or from back to front. In this case, if I just follow the path of the current, it's going to go over. So it loops and it goes over. And therefore, my thumb is pointing in the direction with the north pole. Okay. So this is how we determine that part on the inside now becomes a magnet. But it will have very distinct north and south pole. And this was basically the magnetic field diagrams that you had to understand. Okay, so then the next step was to say, if current creates a magnetic field, can a magnetic field create current? And this was the research that led to Faraday's law. Okay, so I'm just going to basically erase this and just focus on Faraday's law quickly. So they said, okay, if current in a wire creates a magnetic field, does a magnetic field create current? So what they did was, they literally took a magnet. Remember, each magnet always has a north and a south pole. And then they wrapped, I'm going to just make it very simple. Let's make it just one coil for now. And this coil was attached to a galvanometer or a voltmeter. The difference is the galvanometer can be connected in series while the voltmeter cannot. And then they saw that when the magnet was close to the object, that as soon as it stopped moving, there was no voltage. So they thought, oh, okay, so nothing's happening. When they take the magnet away, they see that the voltmeter or galvanometer makes, a deviation. When they bring it back, there's another deviation. So what they saw was, bringing this magnet close to this wire actually induced current in the wire. So a magnet on its own, close to a wire, does not necessarily generate electricity. But moving a magnet and a wire, you can move the one or the other, is going to induce current in this specific conductor. So they experimented with this, and then they added more coils. And then they saw that the more coils they added and the larger the magnet, the more voltage it creates. Then they realized the quicker they bring the magnet in and out of the loop, or cutting into the wire, cutting into the magnetic field, the quicker they did that, the higher the current became, the higher the voltmeter reading as well. So Faraday came up with what is known as Faraday's law of magnetic induction. And this law, by the way, you need to know, which states that voltage or an EMF is induced when there is a change in the magnetic flux, or change in the rate of magnetic flux. Okay, so I want to just rewind this a little bit because I haven't touched on flux yet, but that's where we're going. So what is happening here? Remember, this magnet on its own does have magnetic field lines. So we know magnetic field lines flow from north to south. So what's happening here is when the magnet is brought close to the metal wire cuts into the magnetic field lines. And that is known as magnetic flux. Magnetic flux is basically how much the wires cut into a magnetic field line. Okay? So magnetic flux, for those of you who struggle with this concept, I want you to imagine a big pot of, let's say, stew. And you have a wooden spoon that's as thin as my pinky, and you have to stir it. Okay, that's not going to be very effective. You might get it done quite easily, but the stew will burn because you're not actually creating enough motion, enough flux. Okay, whereas if you use a proper spoon, like a big spoon, and you stir it, larger area, more flux, more motion, more success. So magnetic flux works on how much of the wire is cutting into the magnetic field line, how much of the spoon is cutting into the spoon type of situation. Okay, so what we then did was we said, what is this flux thing? So we said, okay, if you have a coil, and you don't have one magnet, but you just place a magnet on this side. Remember, each magnet always has a north and south. Doesn't matter if it's indicated or not. Magnetic field lines between these two magnets will flow from north to south. So I'm going to indicate this direction. So the magnetic field line strength or magnetic flux density is indicated by the letter B. We measure it in Tesla. This is the symbol P, measured in Tesla. Okay. So how strong the magnetic field is. It makes sense then that when we use bigger magnets that this will be larger. The magnetic field strength will be larger. Then the second thing about this that we have to go and look at is the area of the loop. So if you imagine the area of this loop, let's say the loop was this size. We can clearly see that the smaller the area, the less magnetic field lines will cut through it. So the size of the loop, in other words, the parts of the loop that actually physically cut through the magnetic field line, is dependent on the size or the area. Now for area, I can't give you a specific formula. If it's a circle, pi r squared. It depends. A coil normally. So what we do is then we combine these things, but there's a third element to it, and that is that we need to take the magnetic field lines that are going to be perpendicular to the plane of the loop. I'm going to say that again. When we use the magnetic field lines, we need to focus on the angle between the normal or the perpendicular component to the plane and the magnetic field lines. It's easier for me to just say between the normal and the magnetic field lines, because the normal all throughout grade 11 has been a 90-degree angle with the surface. So if this is the normal, and you can draw it anywhere as long as it's 90 degrees with this coil, we clearly see that the magnetic field lines are parallel to the normal. So the angle between them will be 0 degrees. And this angle is theta. So to calculate flux, we use this formula. This is flux. The symbol is phi. It's measured in Weber. Is equal to V perpendicular times A. Another way of writing this is to say VA and then add cos theta. So V is measured in Tesla, A is measured in meters squared, and this angle is 0 degrees. So when the coil is upright like this, cos 0 gives me 1. That's actually the largest value that it can have, is 1. Cos 0 equaling 1. So then we know that the magnetic flux is at a maximum. I'm going to just make up a value and say that this answer was 100 Weber. Okay, second scenario. Magnetic field lines are still flowing from north to south. The magnetic field strength is still the same. Sometimes they might change magnetic field strength, sometimes they might change the area, sometimes they might change the angle. Okay, so I'm not going to focus on changing the field, changing the area. I'm going to focus on changing the angle. So now I'm telling you that the coil has rotated. The coil is now lying flat or parallel to the magnetic field lines. So I go and draw the normal immediately. It doesn't matter where you draw it. The B is still the same value. This was flux initially. Okay. We then move on and say, what will the angle be between the normal and the magnetic field lines? We can see it's clearly 90 degrees. Cos 90 gives me 0, which means in this position, if this is the final position, if cos 90 equals 0, anything times 0 gives me 0 Weber. Okay. So we see when we want to go back to Faraday's law, changing flux is to be used. What is changing flux? It's final minus initial. And this is going to give me 0 is my final flux minus 100. My changing flux is therefore negative 100 Weber, which is normally going to cancel out that negative sign in front of the number of windings. N is the number of windings. In this case, because it's only one loop, this number will be 1. Otherwise, they will specifically tell you what the number is. Okay, so what we see if we look at this EMF, number of windings, the more windings we have, the higher the voltage. The larger the change in flux, the larger the voltage. The lower the changing time, the higher the voltage. So why are we learning about this? Because in grade 12, you're going to see that this is going to start rotating and spinning. And this is the principle of generation of electricity. So when you spin it quicker and there's a larger change in flux, shorter amount of time, more windings, you can create a lot of voltage. What is used to make it spin at power stations? Normally steam. So coal power stations boil water, the water makes steam, the steam is put under pressure, the pressurized steam turns turbines, the turbines move in and out of the magnetic field, and that's how electricity is generated. Okay, just 2 more things I want to talk about, and then I'm done, and you can ask me any questions you have. If it wasn't in this position, this is the one thing I quickly want to say. Let's say we started off our initial flux, we calculated was 100 Weber. That was when the object was was vertical. Now the object or the loop makes the normal makes a 25-degree angle with the magnetic field lines. So this is going to give me where B is still the same, A is still the same. Cos is no longer 0, cos is 25. And if you calculate cos 25, which we will do quickly, thank you. This is going to give me a value of 0,9, thank you, which is less than 1. If the angle increased to cos 45, it would have given me 0,7. So we see that the more we turn it, the smaller this value becomes. Remember, for 100 Weber, we said it was cos 0 degrees. So we're going from an answer of 1 to an answer of 0,9, 0,7. So we see this becomes smaller and smaller. What does this mean? The larger the angle between the normal and the magnetic field lines, the smaller the flux. Okay, so at this position, cos 25 degrees, let's say I calculated the flux at this position, and it gives me 90 Weber. Because this answer is 0,9, I'm just making up 90 Weber. If I go and I calculate my change in flux, it's going to be flux final minus flux initial. Flux final was 90, initial 100. So my change in flux is now only negative 10 Weber and no longer negative 100 Weber. So basically my change in flux is smaller. So what we want is for this to go from vertical to horizontal very quickly, so that the change in flux is a maximum. And that's why generators normally this thing is spinning, so the change in flux is a maximum. Okay. I want to just relate this to you. If you look at this change of negative 10 Weber, and in the previous example it was negative 100. I want you to imagine joining a Weight Watchers group. I don't believe in dieting or Weight Watchers, but that's the only thing that's coming to mind for me now. If somebody loses 100 kilograms, imagine the applause. Imagine the voltage. Wow, okay. If somebody loses 10, it's like, yeah, we'll see. So the change is not that big. The larger the change, the more voltage is created, based on Faraday's law. That's the one thing I quickly wanted to mention. And then the last thing, which is confusing to learners, is known as Lenz's law. It's the law of playing hard to get. I want you to imagine that there's a magnet, and here's a solenoid, and inside this solenoid is a piece of metal. So this piece of metal can become magnetized. There's a voltmeter connected or galvanometer, it doesn't matter. So when this magnet moves towards, it's moving, it generates voltage, which means there's current flowing. If I now go and look at what will happen, it's going to generate current, and that current that is generated is going to form a north and south pole for this piece of metal on the inside of my solenoid. So it's not magnetized, but because current is not flowing, it will become magnetized. So if this is moving towards this solenoid, when north is moving towards it, there will be a north pole induced on this side and a south pole induced on this side. Okay, which means if I use my right hand rule, north, the current will be flowing from the front to the back, which means the direction of the current will be like this. Okay, so that's like playing hard to get. Somebody who light comes close to you and you kind of want to repel them. But the repelling is, you don't want to be too hard to get. So the magnetic field that is induced is not enough to prevent the current from flowing. Okay, it's just little bit of opposition, Lenz's law. Now, when I move the magnet away from this solenoid, when the north pole moves away, it's going to induce a south pole on this side and a north pole on the other side. Like, no, come back, okay? Which means if I then use my right hand rule, the current will be flowing from the back to the front, which means that the current is then going to flow in the opposite direction. So what we see is when this moves back and forth, it does generate a change in magnetic field, which means that the current is going to constantly move, and therefore the voltmeter will have deviations in both directions. And this is actually alternating current, which is the current that we will discuss in detail. And that's my story. That's a lot to take in, you agree? But I do think it has value tying it all together. Can I just get some